So let's look at some of the data that we've collected to compare the humectancy between sucrose and some of these alternative sweeteners. So how did you set up this experiment, Mary, and tell us a little bit about this table we're going to look at and how to read it?
Right. So we wanted to know, since sugar is a good humectant, how do these other sweeteners compare? And granted, this is just one aspect of what sugar brings to the table, right? So it has a lot of other attributes that are needed in these formulations, but we're going to focus here on humectancy. So basically, when I was talking before about these manual isotherms, we did that for all of our natural sweeteners here. And we were able to produce a relationship between water activity and the moisture content and relate that to in terms of sugar, how well does it compare to sucrose? So we have a sweetness equivalency, so I wanted to kind of put that there. Varying amounts, most of these sugars are, well, they're kind of 50-50 really. Half of them are a little less, half of them are a little more. Based on the relationship that we found in the lab, we're able to kind of calculate how much a mass amount of these sweeteners would we need to replace a similar amount of sucrose. So if we have sucrose and we are looking, we targeted a 0.85 water activity, meaning we made the solution that would give us that specific water activity. So that's what we're talking about for humectancy. How would that compare to sucrose? And so I have this humectancy ratio. 100% would be the same amount as sucrose. And then all the other ones, and most of them are less, it would take less of that sweetener to produce a similar effect, a similar binding effect to the water. So that was a little bit of a surprise because sucrose is known to be a really, really good humectant. And then we turn around and we look at these natural sweeteners and we say, they can actually be better at it than sucrose can. So I found that was really, really interesting. So one of the things I wanted to add on the table too is, okay, so what if we added the same amount of sugar in our formulations? What are we going to get sweetness wise? And so I have this little bit on the end of my table, sweetness for same grams of sucrose. So if we added the same amount of these sweeteners, how sweet are they going to be? And so I just took an average for stevia, so like 160 times as sweet. And it just, I felt, maybe gave another way to look at this data. How, if we just, gram for gram replace sugar, what are we going to get humectancy-wise, and also what are we going to get sweetness-wise? So you can get a similar humectant effect, but you're also going to get a lot sweeter. So all part of that formulation consideration, honestly.
And then we also collected some isotherms on these different alternative sweeteners. This is kind of our bread and butter to look at, the relationship between water activity and moisture content. So let's first look at the sugar alcohols. So that includes sucrose, or we're going to look at sucrose compared to sorbitol and erythritol. So what do we see from the isotherm that you might not see, if you didn't have this data?
Right. One thing that was really apparent is the erythritol. It is so flat. It's very similar. Where above, let's see, about 9.2 water activity, it just goes straight up. And what's happening is this deliquescing, but it's also its solubility limit. So when I was talking before about that crystallization problem that we were finding with erythritol, that's what we would see at 25C. We had to really crank up that heat to get it to go into solution. And as I read some things online, that is a problem, a definite problem. So as we look at this isotherm, we would be able to see that right away, that it's not going to take up much moisture until it gets high enough, it'll finally dissolve at 25C. Conversely, when we look at sorbitol, it does have a more gentle effect, and you can see that it does and did have a good humectant response. So it starts taking up moisture pretty much from the get-go. Around 0.7, it really starts to take off and bind with the water a lot. So that's some easy things we can just learn from looking at this isotherm. And we can also see too, and as I alluded to before, when we did our solutions the other way, our manual isotherms where we're heating up and cooling it down and taking these samples as we're driving off the moisture at this high heat, they correlate. So where that point happens where they start to crystallize, you can see in this isotherm too.
And I maybe should have mentioned that these are adsorption isotherms, so we're looking at the way that water is binding to these alternative sweeteners, and then we can really clearly see inflection points or deliquescence points where these are going into solution. So now let's look at fructose and how it relates to a few others. So we'll be looking at fructose, allulose, as well as tagatose.
Right.
So what are we seeing here compared maybe to that other graph?
Yeah, so this is quite interesting too. You'll notice that if we look at sucrose, which is the blue trace, and tagatose, which is the red trace, they're nearly right on top of each other. So they're very similar in their characteristics between the two. And we are kind of seeing that as well when we were researching it, right? Some of the attributes that tagatose has matched closely to sucrose. As we're looking here, you'll notice that fructose actually has the lowest water activity where it starts to dissolve, so that's nice. So it'll stay in that nice amorphous state. And then allulose is kind of in the middle, so it's around 0.73 would be what I would say. And then we start seeing its response where it starts to take on moisture. And I just wanted, before we kind of leave this topic, just really hit again that the importance of having your sweetener in an amorphous state, because that way it can bind with water. Once it's crystalline, it doesn't, the only way that it'll react with water is on the surface. And so you won't get these water binding capabilities that you would see and desire in something when you're looking for the sweetener. So you must keep your sweetener in an amorphous state.